Welcome back to 6th grade science. So in the last video, we ended on a discussion of friction. Specifically, we ended up talking transfer of electrons, but the last example was friction. When I was talking about polarization right before friction, I was talking about scrubbing your feet along a rug and how electrons go from the rug to your feet. And then I talked about balloons and friction and scrubbing them on your head. You probably thought I was a little crazy because I kept talking about friction and polarization, but every time you've done those things, or when you reach for a doorknob and get shocked, or you have a blanket that you touch at night and you see sparks, you think of that as static, and you're correct. So today, we're going to talk a little bit about static, and more things as we continue our discussion about electricity. So like I was just saying, friction causes static charge. In the example of polarization, I was talking about the electrons moving from the rug to you, and then the electrons in the door handle rearranging. But in order for the electrons to go from the rug to you, friction occurs. So friction, remember, occurs when things are rubbing together, creating friction. The electrons move, and then from there you can have static charge. So when you are rubbing the balloon on your head, or you're rubbing your feet on the rug, you are moving electrons to you. You hold on to those electrons because with static charge, or with charge in general, items that are charged typically remain charged until they come into contact with something else. Something to remember though is it doesn't necessarily have to come into contact with something. It could just be really close. Problem with the really close part is electric charge does not necessarily travel super well through air. The drier the air, the less likely electrons are to travel through it. But Mr. Morgan, during thunderstorms, lightning travels from the sky to the ground. We'll get into that later. When I referenced static, and I referenced touching the doorknob and getting shocked, or I referenced touching the blanket and seeing sparks, these are static electricity, but it's not just static electricity. It's also known as, or specifically known as, static discharge. To give static discharge a definition, it is a sudden flow of electrons, which in the PowerPoint tomorrow when you look at it, you'll notice it's a little E with a minus sign above it. That's how you write electrons shorthand. Protons that we talked about in the last video are P with a plus sign above it. With static discharge, the sparks that you see or the shock that you feel is from that. If electrons don't move well through the air, then how does lightning occur? During a rainstorm, you have a lot of different moving components, and I don't necessarily mean the wind blowing the trees. Up in the clouds, you have moving air particles, water droplets, ice particles. And all of these things moving around in the clouds cause the clouds to get regions of negative area and positive area. Now remember, these are negative charges and positive charges. The negative charges are concentrated at the base of the cloud down by us. So when you look up at a cloud, you're looking at the base. The positive charges tend to gather around the top of the cloud. Remember in the door handle example, when I brought my hand closer to the door handle, my negatively charged hand caused the electrons and protons to rearrange in the door handle. When you have the cloud base becoming negatively charged, it causes the protons and the electrons in the ground to rearrange. Remember our discussion on electric fields and electric force. The closer that an item is, the stronger the field is. Or in this case too, the stronger the force is. So when you have lower level clouds that are closer to the ground level, it will have a stronger impact. Also remember though, the more you have, so if you have a lot of negative charges, it'll be a stronger field and force. So the rearrangement occurs in the ground so that the negative electrons move further away and the positive protons are towards the surface of the ground. The atmosphere holds the negative charges and the positive charges in place, so it restricts the flow of the electrons from the base of the cloud to the ground. Remember our discussion about protons in the nucleus and how there are forces inside the nucleus that squish the protons together even though they want to repel? There are other forces in the atmosphere that help hold the negative charge up in the clouds and the positive charge down in the ground. As more and more charges build up, the air between the negative charged cloud and the positive charged ground starts to also become charged. And eventually it gets to the point that you have a lightning strike. And all lightning is electrons moving from the negatively charged area down to the positively charged area. Lightning is a quick, or rather relatively quick, example of electrons flowing from point A to point B. But it's not a continuous flow of electrons. When you have a continuous flow of electrons, that's known as a current. Remember when we talked about wavelength and frequency, and how frequency was how much movement occurred over that 1 second period? Electric current is a similar idea to that. It's measured as the amount of charge that flows past a certain point within a given period of time. And we've talked about different SI units for things. The SI unit for electric current is the ampere, which is a capital A, or amps. We've talked a little bit about this, but you can have direct current or alternating current. Remember that direct currents move from point A to point B in one direction, whereas alternating currents move from point A to point B, back to point A, back to point B, so on and so forth. It's reversing directions constantly, so it's an alternating current. Bringing back something that we haven't talked a lot about, potential energy. Just like you have potential energy with other things, you also have electrical potential energy. This comes from where the charged particle is in the position of the electric field. Electric charges always move spontaneously from an area of higher potential energy to lower potential energy. So for an electric charge to move from point A to point B, there has to be a difference in potential energy, specifically a difference in electrical potential energy between those two various positions. This is known as voltage, which is specifically the difference in electrical potential energy between 2 points. The SI unit for voltage is the volt, which is represented with a capital V. We've talked about static electricity, static discharge, lightning, and then we talked about current types, which we've spent quite a bit of time on throughout this semester so far, and voltage. Now we're going to talk about cells. And I'm not talking about the type of cells that are found in you and me. I'm talking about chemical cells and solar cells. What's a chemical cell? Well, they're found in batteries. So on whatever device you're using to watch me right now, it likely has a battery. And that battery inside has chemical cells that convert chemical energy into electrical energy. Solar cells, when we get into it, take energy from the sun and then turn it into electrical energy to charge your devices. Chemical cells produce voltage through use of chemical reactions. And what's voltage? It's the difference in electrical potential energy. Chemical cells have 2 electrodes in them, and these electrodes can be made from things such as zinc or copper. An electrode is something that can conduct electricity, and it goes into non-metallic solids, liquids, or gases. These electrodes are suspended into some type of electrolyte. Electrolytes are substances that carry free ions that can carry an electric current. If your electrolytes are in a paste, that's what's known as a dry cell, whereas if your electrolytes are in a liquid, that's considered a wet cell. A real-life example of a chemical cell that contains a dry cell is the batteries in your flashlight. A real-life example of chemical cells that contain wet cells are your car batteries. Or more specifically, car batteries, not necessarily your car batteries unless you're driving at a really early age. Both dry and wet cells work basically in a very similar way. So for all intents and purposes for this video and this class, we're going to consider them the same. The electrodes in the cell react chemically with whatever electrolyte solution that they're in. This causes one electrode to give up electrons and the other electrode to accept electrons, which makes one side negative and one side positive. Electrons can then flow from the negative side to the positive side. The electrodes extend out of the battery, which allows you to connect things such as wires, which will charge whatever device or give power to whatever device you're working on. So if it's a flashlight or a remote control, you have the negative side of the battery and the positive side of the battery. When you put it in the remote the right way, it completes the circuit. Then the chemical reactions that are occurring can produce electricity for whatever device that you just put the batteries in. That was chemical cells, and Before I mentioned we were also going to talk about solar cells, so let's talk a little bit about solar cells. Like I said before, a solar cell is something that converts sunlight into electrical energy. This is also called a photovoltaic cell, or a PV cell, and it's because it's broken down into the words. So you have photo, sunlight, and voltaic, voltage, come together to make photovoltaic, or a solar cell. Solar is easier to say. These are made from things such as silicone, which can absorb light energy. The new energy knocks electrons loose within the material itself. This allows them to flow freely, and when they flow freely, it in turn produces a difference in electrical potential energy. This flow of electrons in the material causes electric current. Solar cells also have a negative and a positive contact point. This is just like the terminals in chemical cells. If you connected those contact points, both the negative and the positive, with wire, say to a light bulb, you could use the solar energy to turn the light bulb on because you're converting sunlight into electrical energy, and you're completing the circuit by connecting the negative side to the positive side to the other item. So the electrons can flow freely from point A on the negative side to point B on the positive side and then repeat. Unless it's an alternating current, then it goes point A to point B, back to point A. All right, that is everything new I have for you today. Some of the stuff like direct and alternating currents we've already talked about previously, and some of it was new information. As always, if you have any questions, please reach out to your teacher, whether that's Miss Cameron or myself. Bye!